A microcontroller acts as a high-speed logic center, but it lacks physical strength. It operates on low-voltage signals that cannot directly power the heavy electrical loads required by a motor. To turn digital intent into physical action, you need power electronics. A 5-volt signal cannot jump the gap to drive a 24-volt motor on its own. Instead of burning off excess energy as heat, PWM rapidly cycles the power on and off. By changing the width of these digital pulses, you adjust the average voltage hitting the motor, creating a highly efficient electronic throttle. Mastering these electronic bridges is the absolute prerequisite for turning any line of digital code into coordinated physical motion. Speed is only half the problem. Controlling the direction of a DC motor requires a specific transistor arrangement known as an H-bridge. This shows the forward state. Closing a specific diagonal pair of switches flows current from S1 through the motor to S4. Reversing the motor requires closing the opposite diagonal pair. Now, current flow is reversed, moving from S3 to S2. This setup introduces a fatal hardware risk called shoot-through. If switches on the same side close simultaneously, they create a direct short circuit. To prevent this, engineers program in a mandatory dead time delay between switching states. Because the risk of a short circuit is so high, engineers rarely build bare H-bridges from discrete parts. Instead, they use integrated driver ICs, like the L298N, to safely manage the switching logic. Stepper motors add another layer of difficulty because they do not spin freely. They require precise sequential electrical pulses to move in distinct increments. A unipolar stepper driver uses simple transistor switches to move the rotor by pulling center-tapped coils to ground one by one. Bipolar steppers are more complex. Without a center tap, the driver pushes current through the entire coil, requiring a dual H-bridge setup. Servo motors function differently. They rely on internal closed-loop feedback, meaning they only need a single PWM line to dictate their exact position. Ultimately, the complexity of your driver circuit scales with the magnetic sequence required to spin the motor's rotor. Industrial AC motors present a different challenge. Their speed is naturally locked to the frequency of the power grid. Breaking that lock requires a variable frequency drive, or VFD. A VFD works in stages. The rectifier converts incoming wall AC into raw DC. That energy is stored and smoothed inside the DC link. If input power drops, the capacitor provides the energy to keep the drive stable. In the final stage, the inverter uses high-power IGBTs to chop that stored DC energy back into three-phase AC at a customized variable frequency. Converting AC to DC just to turn it back into AC is the only physical way to decouple an industrial motor from the rigid timing of the power grid. Modern drivers face a constant trade-off. While higher PWM frequencies make motor control smoother, they also increase the energy lost inside the transistors. This is the reality of switching loss. Every time a transistor flips on or off, a small amount of energy is lost as heat. If the frequency is too high, the hardware will overheat. Inductive kickback poses another threat. When a motor's magnetic field suddenly collapses, it fires a high-voltage spike back into the fragile control circuit. Flyback diodes act as pressure relief valves. They provide a safe path for that dangerous inductive energy to dissipate without hitting the transistors. A well-designed driver circuit serves as a defensive shield, protecting fragile logic chips from the violent electrical physics generated by the motor itself. On a two-wheel differential robot, the microcontroller handles the logic, while a dual H-bridge routes raw current from the batteries to the wheels. To turn the robot right, the controller stops the right motor while driving the left motor forward, which forces the chassis to pivot. In summary, DC motors rely on H-bridges and PWM. Steppers require sequential pulsing, and AC motors need variable frequency drives. Digital code dictates the pattern of movement, but the raw physics of power delivery and thermal management determine if the machine